Thanks for joining us, everybody. We have nearly 100 registrants today. Uh, if you are here for the Energy 101 on hydrogen, you're at the right place. You can see on your screen our agenda for today. Today we're going to start off with some words from Anthony Armley. He's the federal coordinator for the Regional Workforce Initiative, and you'll hear a little bit of background about the Regional Workforce Initiative if you haven't heard about it before. Then we're going to jump right into the main presentation, our Hydrogen 101 talk. And again, just some logistic stuff. Please mute yourself if you haven't done so already. And the slides should be available at some point on our website after the webinar is completed. So with that, once again, this is Energy 101 webinar series. This series was designed to give people a kind of like a 360 look and a non-technical look at some of the very technical and very interesting research and development that's occurring at NETL and the other national labs. We have an archive page where we will put the slides on, which I just mentioned. We've done 101s on modeling and simulation, sensor technology, storage, workforce of the future, jobs data, advanced manufacturing, and others. And this year we have an exciting lineup, and we can't wait to share with you some of the other Energy 101s we will be doing throughout the year. So with that, Anthony, are you ready to go?
I'm ready. Thanks.
Great.
Okay. Good morning, everyone. My name is Anthony Armley, Federal Coordinator of the Regional Workforce Initiative. Many of you have joined us in the past for these types of webinars, but I did notice on the registration list that there's a few new. So what I'll do is I'll just give a quick intro to those that are new, and I'll give a quick update for those who are familiar with NETL and one of our initiatives that we've progressed on. So the NETL Regional Workforce Initiative, we kicked this off in 2017 in support of the administration's priorities to help scale Americans and promote STEM in the workforce. And so we're doing that from a regional perspective where we focus on Appalachia. You can go to the next slide, Matt. Yeah, so the mission really of this initiative is it's an extension of the NETL mission. We're trying to get technologies to market. We're focusing on it from a regional perspective. Specifically, this region that we focus on is the Appalachian region. Two of the three labs at NETL are located, one in Pittsburgh, Pennsylvania, which is where I'm at. The other is in Morgantown, West Virginia. Of course, both of those labs are in the Appalachian region. We do have a third lab out on the West Coast. That's Albany, Oregon. And that's where we do a lot of our materials research. Next slide, please. Snapshot of some of the metrics, just to give you a feel for the growth that we've had with this initiative. Since inception, we've obviously started from zero, and right now we have a reach of over 800 individual stakeholders, hoping to get that over 1,000 by the end of 2022. We connect with over 400 different organizations and institutions, many of which are on the call today. In the past year, we've had over 1,100 registrants to our webinar series. The different types of webinars we host are the Energy 101 series, which you're on today. That's where we take the technical topic, introduce it to a high level, at a high level to the audience so that they have a basic understanding of some of the research that we do at the lab, why it's important, any workforce implications in the future or job implications where this said technology could lead to future jobs in this region. And then we have a monthly e-note. If you're not subscribed, you can go to our RWFI webpage. I'll link that after I'm done talking here in the chat, and you can scroll down and there's a button you can click to opt in. We send that out monthly. We have nearly 300 that are subscribed to that now. And in that e-note, a couple things of note, we list a ton of funding opportunity announcements, especially if you're in that business of going after funding and you don't have time to sit there and look all day for different opportunities. We basically give you a one-stop shop every month of new funding opportunity announcements that you may not be aware of. We also talk about high-level newsworthy items coming out of the lab. We also have a workforce metrics report that we put in there each month. And yeah, any upcoming events, we also try to list in there. Next slide, please. Key outcomes to date since inception, just the establishment of growing the regional network of stakeholders on behalf of the lab, introducing folks that aren't familiar with NETL, what we do here, We integrated a workforce work plan, which I'm going to talk about in the next couple slides, and just growth of partnerships on behalf of the lab. I think using this as a forum to convene the region has been extremely beneficial, and not only for NETL but for our stakeholders as well. Next slide, please. So this is the Workforce Readiness Plan pilot that we started in 2021. It is now officially complete. What it is what we're looking for is any technology at the lab that's 3 to 5 years from commercialization. We wanted to create a workforce template that our technology manager or program manager involved in that research could fill out and provide back to us. And so what it is 4 questions, and we're looking at what occupations would be needed to support that technology in the workforce, and what unique skills or education would be required for those occupations. Essentially, we're future casting here. The effort here was just to better understand the occupations, the trends, and then the skills that would be necessary in the future. That way we can share that with our stakeholders, really anybody that would be interested, from the university level to the community and technical school level, so that they can be more informed. I'm on some different workforce working groups across the Department of Energy, and what we've found is there's a disconnect between academia and industry or the utility sector at times, and that's just because I think technology is advancing so fast that the employers have to adjust on the fly. But the problem is the people that they're hiring aren't getting that up-to-date, up-to-the-minute type of skills in their training. And so what they're saying is that anyone we hire, we have to spend 6 months to train them on some of the new things, on the trends, the latest that we're seeing. And I'll give you some examples of that in the coming slides, what I mean by that, because we've been able to see that from this pilot plan that we put together. One other item of note is that Department of Energy, they're actually now requiring a statement of job creation on all funding opportunity announcements. That started last year, and I think that's a step in the right direction to help mitigate this issue. Next slide. So what you see here is just the box on the left is the four parts to the workforce work plan. So you'll see the job and career field name, the skills that were identified as being needed to support that job, and then any educational requirement that the person filling this out felt would be desirable or needed to get that job, and then availability of any training programs that they're aware of. This allows us to look at this. So we took all of the information. We had quite a few of these. We put them into a database that we created. And then from there, we created a technical report that's in the approval process right now at the lab. It's basically almost done. And then once it is, we're gonna link that on our RWFI webpage, and then you can download the report. It's like 8 or 9 pages, and it basically summarizes all the data that we've gathered in the past year on this stuff and looking at the trends. So the box on the right, you can see is about skills involved in welding. So we took this as a snapshot from our database. As you can see, the employers are going to be looking for more skills for welders. So when you think of welding, you think of literally welding items together to increase strength for that. But what we're finding is from this, and remember, we're looking at this from an oil and natural gas perspective, because that's what NETL's mission is, right? To advance technology in that space. Not the only thing we do, but that's kind of our bread and butter at this time. So you can see that welding is the skills they're looking for is growing. But what we're excited about from this whole work plan is just the breadth of knowledge that pertaining to the skills needed to support these evolving occupations. Going forward, we think this type of work with this project across the labs could be really beneficial, especially for the academia sector. When you think of solar, wind, hydrogen. So we don't want to do this just from NETL. We would love to implement this across the labs. And I think once I can take this final technical report and start pitching this to all the different labs, I think this is something that would be like the next phase that we'd like to try to implement across all the labs. Next slide, please. So in the green here on the left are the top 20 occupations. Of the 58 unique occupations that we gathered from this pilot, we had 20 that we saw multiple of. And so, I mean, I'm not going to read through each one, but but what you're seeing here is there's many occupations in the top 20 that require a four-year degree, but also many which don't require the four-year degree, maybe a certificate program or a 2-year technical type program that we're telling you, hey, in the next 3 to 5 years, when these technologies that we're working on are going to go into the workforce, we need these types of skilled jobs to be able to support these high-tech endeavors. The snapshot on the right was something that I took from the Bureau of Labor Statistics, just taking 2 from that list: chemical engineers, and then the other one was just like welders, cutters, solderers, etc. Kind of pulled them randomly from the list, but it shows the job outlook out to 2030 is really strong. I mean, so you take, professional degree with chemical engineering, and then you take something that might be more technical. They're both showing, a lot of growth in the outlook. And so I just wanted to show that as a snapshot. You would see that from really all of these, though. The advanced skills are really something that's picking up. Construction industry, electricity generation, all of this type of thing, they're looking for advanced skills, and that's what we're finding from this pilot. Next slide. So just to summarize, I want to pass it on here soon to Nate to get talking about the hydrogen, but I'm really excited about this pilot we did because we're finding a lot of good information. Again, the skilled technical workforce, it's a big piece to the high-tech workforce in the future, not only now, but really in the next 3 to 5 years. Technical workforce occupations, very in demand, and there's a misconception because they're pretty good paying jobs. And we're seeing that when you look at all these Bureau of Labor statistic numbers, when you go look at these skilled positions, 20, 30, 40 bucks an hour, good money out there for these. And I don't know that a lot of the younger generation realizes that today. So that's really just the gist of it that I want to talk about. One more slide here before I pass it on is later today from 2 to 3 p.m. As you know, NETL is leading the Interagency Working Group on Coal and Power Plant Communities. They have created a clearinghouse, a one-stop shop for all the funding opportunities that are out there to help communities. And I was checking it out recently. It's awesome. I mean, I think there's over 60 right now that are out there, and you can filter, you can sort for different ones that might apply to you. And they're going to talk about that today from 2 to 3 p.m. So pretty cool stuff, and a nice development that they've created there with the clearinghouse. My last slide here is just my contact information. If you have any questions or thoughts, please feel free to reach out to me. And I'd like to pass it back to Matt. Really excited about today's Energy 101 topic with hydrogen. So thanks, everyone.
All right. So thanks, Anthony, for that great wrap around for Energy 101 and RWFI and the IWG.
Thank you. So, again, my name's Nate Wyland. I'm Senior Fellow at NETL. As Anthony was discussing, NETL is both research organization and also funds a lot of research, external research for folks. So I would sit on the research side of things, but here to talk to you today about some of the basics of hydrogen, some of the research going on at NETL, and then I'll also talk some about the various types of activities going on within the federal government surrounding hydrogen recently, hydrogen hubs, RFIs, etc. So we'll get to talk about that towards the end here. So just to set the stage here with a quote from our Secretary of Energy, Granholm. And we have the tools to put America on an irreversible path to achieve a net zero carbon emissions by 2050. For those who may have heard, the administration, Biden administration, has some very, I would say, aggressive goals with regards to decarbonization. They're looking for 50 to 52% reduction in economy-wide greenhouse gas pollution by 2030. And a carbon pollution-free electricity sector by 2035. So not a lot of time to get to meet those goals. Included in that is addressing some environmental justice and job creation issues. We'll see that with some of the hydrogen hub and infrastructure bill actions that have been taken. And then kind of the ultimate goal is reaching a zero carbon economy by 2050. Again, really aggressive. Would require an awful lot of infrastructure awful lot of new jobs and energy, which is why we're here today. So the hydrogen piece, I'll say hydrogen is essential to meeting some of those ambitious goals, zero economy goals, in particular because it's very useful for decarbonizing some difficult to decarbonize sectors, and we'll get to that piece in a little bit as well. Let's move on. So the hydrogen economy, so most of what we see on the left-hand side of this slide, it's kind of the typical energy infrastructure right now. We're electric grid that has renewables, nuclear, coal, natural gas, et cetera, feeding into that. But to stem off of that, we might utilize some of that electricity or even some of the coal or natural gas specifically to generate hydrogen, which can be used for a lot of different purposes. We can, in particular, generate power again from that hydrogen. So as a way to sort of offset, say, renewable power that's generated during the day, we generate hydrogen, and you can use that hydrogen to generate power at night or in the wintertime when we don't have as much wind or solar power. Hydrogen can be used in vehicles, can be used to help make synthetic fuels, help upgrade biomass into oils and the like. It's also a primary component for fertilizer, ammonia in particular, which in itself is a carbon-free fuel. And we'll talk a little bit about that as well. Hydrogen can be used in metal refining and for other end uses. And it's really kind of those, the blue, purple circles there are where hydrogen is very useful in helping to decarbonize industries that really don't have a lot of alternatives for decarbonizing. So what is hydrogen? It's the lightest of all the gases, very versatile, very clean, and a flexible energy carrier, and produced from a variety of domestic resources and usable as shown here in a lot of different applications. So I'll note most of today's hydrogen comes from natural gas. It's about 75% of the world's hydrogen comes from natural gas currently. Most of the rest comes from gasification of coal, although a lot of that happens in China. But there are a lot of other options for generating hydrogen. So solar and wind power to generate electricity certainly can use that electricity through an electrolysis process, essentially splitting water into hydrogen and oxygen to generate that hydrogen. Likewise, you can use nuclear power in much the same way, utilizing the electricity from nuclear power to generate hydrogen as well. There are a few other processes that are very specific in terms of geothermal or biomass-oriented processes to make hydrogen as well. I've already mentioned most of the hydrogens produced from natural gas, and the primary production method is through steam methane reforming currently. It's the one on the far right. So steam and hydrocarbons, typically natural gas, are come together under high temperatures and pressures to generate hydrogen in that case. So other options, I've already mentioned the gasification, mostly a conversion of solid feedstocks, coal. We could also utilize biomass or even waste plastics to help generate hydrogen through a gasification processes. And then, as I've mentioned, electrolysis processes are, again, taking electricity to split water into oxygen and hydrogen. And I also mentioned the direct solar water splitting, where that sunlight can be used to help heat water molecules and split again into water, hydrogen and oxygen again. So finally, I've already mentioned this can be used in a lot of different sectors. Fuel cell vehicles, there are a number of, light duty electric vehicles are running on hydrogen, primarily in California. I think it's likely, or I think the industry is sort of recognizing that battery electric vehicles are probably a better fit or a better option for consumer or light duty electric vehicles. However, for heavy duty vehicles, hydrogen is a much better source because it's you're able to refuel much quicker rather than waiting for a battery to charge, for instance. So in sectors like heavy duty trucking, rail, and even in some cases shipping or aviation, hydrogen might be a better fuel here. There are very good hydrogen is good as an energy storage medium. As I mentioned, the sun doesn't always shine, the wind doesn't always blow. You do need to wait to store that energy. There are batteries for kind of short duration storage currently, but hydrogen is looked at as a viable or very good option for long duration energy storage on the order of weeks to months. So, I've already mentioned fuel cells. There's a lot of interest from cell towers, data centers, hospitals, supermarkets, people looking for backup power, where hydrogen fuel cells can provide not only a steady source of power, but a very reliable source of power. Fourth bullet there, the hydrogen is one of the primary uses for hydrogen today is in the petroleum refining markets. So there is actually already a network of hydrogen. There's a hydrogen pipeline along the U.S. Gulf Coast. Again, the primary use for that hydrogen is in petroleum refining. And I'd say the second largest use would be in production of chemicals. Ammonia is one of the major chemicals produced from hydrogen, and again utilized primarily for fertilizer production. Hydrogen is great, does a lot of different things, but it does have a couple of challenges that we need to overcome, and hence the need for a research program and kind of a national strategy on how to fix that. So energy density is one of its biggest challenges. So on the left-hand side, you can see, on a unit weight basis, hydrogen's about 3 times more energy content by mass than say gasoline or diesel or even natural gas. However, it's a very, very light substance. So if you want to put that on a volume basis, it has about 4 times less energy content by volume than gasoline. So if you're looking at a vehicle, for instance, with a specific size tank to hold your fuel, you need a 4 times larger tank to carry the same amount of fuel energy with you, utilizing hydrogen. So that is one of the primary challenges. Another big challenge is economics. Clean hydrogen is really expensive currently, but there are some research programs going on now to bring those costs down. As I mentioned, sort of on the left, we have natural gas and coal. Those are really the primary production technologies for hydrogen right now. About 2% of the world's hydrogen is made from biomass and electrolysis from electricity produced through nuclear, solar, or wind processes. So not a lot right now, but certainly need to increase those numbers. Hydrogen production costs, you can see on the right here. You'll notice SMR, steam methane reforming, which I've mentioned already. And I'll note as well the CCS is with or without carbon capture and storage. So again, the main goal here is to decarbonize. So in this case, you're taking methane, we're reacting that with water to generate hydrogen and carbon dioxide. That carbon dioxide is captured and stored typically in underground reservoirs. So that tends to add a fair amount to the cost. So you're seeing some costs here with and without carbon capture and storage, or CCS, for both SMR and coal gasification. I'll note that this particular slide is, I think, utilizes some dollar figures, or I should say cost figures from Europe, where they tend to have higher natural gas costs than in the United States. So actually in the U.S., the top 2, steam methane reforming, has a better hydrogen cost profile than say, coal gasification with or without CCS in the United States. And you can see in the bottom, nuclear electrolysis, solar, wind electrolysis, very high costs currently. The electrolyzers themselves are high cost, but then we also factored into this is the fact, again, that the sun doesn't always shine and the wind doesn't always blow. So in order to produce the same quantity of hydrogen, you need to have a much larger build out of solar or wind on say, a megawatt capacity basis to generate the same amount of hydrogen. So that factors into this cost as well. So just as a point of reference, on the green box in the upper right. If a goal is to get down to $1 per kilogram of hydrogen, it's about $7.40 per MMBTU. Typically, prices for natural gas nowadays in the U.S. are somewhere between $2 and $4 per MMBTU. So, yes, we are paying for more for that hydrogen energy. We're paying essentially for that decarbonization. So, taking the carbon out of the methane, storing that underground, and transporting that hydrogen for end use in a decarbonized manner. So note the Department of Energy has started an energy Earthshot, sort of like to take off on the moonshot as from the 60s to get us to the moon. The first energy Earthshot was based on hydrogen. So the main goal here being to produce $1 per kilogram clean hydrogen within 1 decade. So that's going to require about a 5-fold increase in clean energy use and reduction in clean hydrogen costs by 80%, at least on the electrolyzer side. Cost reductions are lower for the fossil fuels technologies, but still have a ways to go there as well. So in reaching this goal, we're expecting that to have about $140 billion in revenues that come out of the new hydrogen industry. About 700,000 jobs that can be created here by 2030. Another quote here from Jennifer Wilcox. She is the Acting Assistant Secretary for the U.S. Office of Fossil Energy and Carbon Management. Sourcing low carbon hydrogen will be critical to producing fuels and chemicals with CO2 as a feedstock. Potential for applying carbon capture to help advance a low cost and low carbon hydrogen economy. So that's what we're doing at NETL. Our main role is working with the Office of Fossil Energy and Carbon Management, although we do work in some regards with other agencies as well. But being the primary fossil energy laboratory, it's kind of incumbent on us to enable this rapid and cost-effective transition to a hydrogen economy. As I've mentioned, we've already got many, many decades of research in carbon capture and storage, as well as a lot of work on fossil fuel, large-scale fossil fuel production, infrastructure, power systems, et cetera. And of course, do a lot of R&D to help on hydrogen, which I'll show in a minute, across the entirety of the hydrogen value chain. So on this slide, I'm just showing the different pieces of the hydrogen value chain. So all the way from production to transport and storage and utilization of that hydrogen. On the top, we'll see that electricity from wind or solar or nuclear that's used in electrolysis to make hydrogen is often referred to as green hydrogen, whereas anything that's generated from fossil fuels, if it includes carbon capture and storage, would be referred to as blue hydrogen, and that's primarily where NETL is working. We do some work on electrolysis as well, mostly from electricity produced with carbon capture from fossil fuels. However, on the far left, we have we're also able to take coal and biomass, waste plastics, run those through, say, gasification processes or chemical looping processes to create blue hydrogen. As I mentioned, natural gas reforming processes like steam methane reforming can also produce blue hydrogen, and all of those utilize carbon capture and storage. There is another route that I'll talk about briefly. It's natural gas pyrolysis, essentially heating up natural gas in the absence of oxygen to create hydrogen and solid carbon co-products. Really interesting technology, which we're also working on. But once that hydrogen's produced, it really doesn't matter if it's blue or if it's green. It's just the, where it comes from. So, hydrogen's hydrogen, and there's a lot of different ways to transport that. You can do, typically it's done through road, rail, or marine transport. There, as I've mentioned, is a single hydrogen pipeline throughout the Gulf Coast that connects a lot of hydrogen production facilities to primarily petroleum refineries. However, we might endeavoring to expand our hydrogen pipeline into more of a national network similar to our natural gas infrastructure. Alternatively, you could blend hydrogen into our existing natural gas pipeline. There are some safety and material compatibility issues that would need to be worked out, but current thought is that you could blend up to about 20% hydrogen into natural gas without creating too many difficulties or having to retrofit things too much. So, but important in both of those instances, or how do you do storage? We currently do natural gas storage in large underground reservoirs, either depleted natural gas reservoirs or purpose-built natural gas reservoirs. How do we also do hydrogen storage in a similar fashion, or co-storage of hydrogen and natural gas? One other item is you can take that hydrogen and convert it into ammonia or other hydrogen carriers to more easily transport it. Finally, whether that's, in the form of ammonia or hydrogen or a blended hydrogen and natural gas mixture, how do we utilize that hydrogen in the transport sector for industrial use, refining, making synthetic fuels, et cetera, power production, heating, et cetera. So I'll get into a little bit of our work in each of these segments in the coming slides here. So first, starting off with production. As I mentioned already, coal and natural gas are really our primary sources of hydrogen today, and the work that we do is really working on improving the efficiency and the cost effectiveness of that clean hydrogen production, again, trying to incorporate the carbon capture and storage pieces to reduce its carbon intensity there. So we're doing that in a number of ways. So we have just giving a couple of examples of the types of work that we're doing at NETL in terms of research. We are looking at some advanced natural gas reforming technologies. The one on the left, actually utilizing microwaves to assist in that reforming process to move you from methane to hydrogen through a number of different routes. I've mentioned already that electrolysis can be used. There are a couple of different types of electrolysis. Solid oxide electrolysis cells, or SOECs, are something that's we've utilized, or I should say we have a lot of expertise on within NETL, similar to a solid oxide fuel cell. They're the more higher temperature, I should say. They're higher temperature fuel cells and therefore more efficient fuel cells or electrolyzers than some of the lower temperature cells that are currently in production. Note that we've also done a lot of work on multi-phase reforming and gasification with some inherent carbon capture systems. I mentioned the chemical looping systems already. I mentioned as well the methane pyrolysis for hydrogen and solid carbon co-products, where you can make nanofibers, nanotubes, nanosprings, graphene, carbon black that's used in rubber tires, for instance, a lot of different things there. So it avoids the need to make CO2 and then store that underground. Instead, you're making solid carbon products where you don't need to handle that CO2 specifically. Then on the far right, I've mentioned we have a co-gasification. We've done a lot of work on gasification through the years of coal, but also looking at co-feeding biomass and waste plastics in order to generate hydrogen as well. I'll note that we're leveraging a lot of our parallel research in the transport and storage aspects in order to improve hydrogen transportation costs. So transporting it long distance, with bulk hydrogen really does have create a major barrier to a hydrogen economy, because that is costly due to its low density. But because of our work in natural gas infrastructure, we're able to leverage some work to solve some of the R&D challenges there. I've mentioned the ammonia production already, or ammonia as a potential hydrogen carrier. We have a novel microwave-based ammonia production process. It's a really fabulous technology. It's a shift from the large-scale, high-temperature, high-pressure ammonia production plants to something that's done at atmospheric pressure and with a microwave, so that really can help you modularize and shrink the size of that ammonia production process, such that it's usable, at the base of a wind turbine or at a solar farm level. Mentioned as well, we're working on hydrogen carriers. There's a lot of different types of hydrogen carriers. On the slide shown here, we have some microporous carbons generated from coal, where the hydrogen penetrates into the pores of that coal structure, absorbs onto the surface, and is used to improve the storage capacity for hydrogen transportation. Do a lot of fundamental materials research, not only for hydrogen material compatibility, but also materials for separations of say, hydrogen and carbon dioxide. Using some of those similar materials, technologies, a lot of that goes into sensors for real-time hydrogen safety, pipeline monitoring, monitoring of plants, for instance. We have a kind of a suite of sensor technologies for that, which I won't get into today. As I mentioned, we're also working on some subsurface hydrogen storage in permeable rock formations. Hydrogen is stored in salt caverns, underground salt caverns. Currently, there is a very limited supply, however, of salt caverns around the country. So we are looking at other options, other geologic formations where you can store hydrogen throughout the country to make that more ubiquitous, I should say, throughout the U.S. and throughout the world. So, in terms of end utilization, we do need some new technologies. We also need some retrofit technologies to efficiently utilize that hydrogen and potentially hydrogen natural gas blends, if that's the form of our hydrogens coming in. We do a lot of work in hydrogen gas turbine combustion. In particular, what happens to your combustor as you add hydrogen to the natural gas, for instance. The second technology, rotating detonation combustion, is actually very interesting. It essentially utilizes kind of the high reactivity of hydrogen to make a detonation that spins around in this annulus and creates a pressure gain that can be used to add power to a downstream turbine. So it is a way that hydrogen can be used in a gas turbine and also would give you a power or efficiency increase as well. I've already mentioned some of our work in solid oxide fuel cells, which can utilize hydrogen to make power. We can also utilize those fuel cells and integrate them with other systems, gas turbines, IC engines, et cetera, to make even more efficient systems. And how to put those pieces together so that the controls work and we don't exceed the limitations of any specific piece of equipment. So a lot of work done at NETL on those pieces. And then finally, utilizing hydrogen as a feedstock for chemical synthesis, another piece of work that we do. We do a lot of work as well on systems analysis across the entirety of the hydrogen value chain. We're trying to minimize the cost, bring the cost of hydrogen down, also trying to reduce the greenhouse gas emission profile, reduce the carbon intensity of that hydrogen from a national perspective. So, and we look at that through the entirety of the hydrogen value chain. So, a lot of work on modeling, techno-economic analyses for the hydrogen production methods. I've mentioned as well the solid carbon co-production from methane pyrolysis, where we're looking at market assessments of the costs and utilization of some of those solid carbon products. We have a study that's ongoing, should be coming out within the next month or two, on assessing a regional hydrogen infrastructure build out and job impacts. In particular, this particular study is on the Appalachian region. But we do have some similar studies going on in other regions of the country, like Four Corners, Arizona, New Mexico region, for instance. The last one is, I would say, life cycle analyses, which is used to determine greenhouse gas emissions, which includes CO2, methane, et cetera, to sort out or reduce the carbon intensity of the hydrogen that's produced in this case. So, last thing I'll note here is this, anything that we're doing is sort of highlighted in green here: production, storage, transport, use. it really plays to NETL's strength. So any of the R&D that's funded through NETL is going to result in job creation for these technologies. We need jobs to help develop them. We need jobs for the engineering and design firms to advance the R&D on those technologies and get them ready for commercialization. And finally, once they're out into the marketplace, certainly need people for the construction of those plants and operation as well. So, and I'll get into that in just a moment here. So, one thing I'll note, or sort of shifting gears a little bit to from NETL to a larger DOE perspective, if we're trying to get hydrogen out into the national economy, how are we going to do that? So the Department of Energy put out a Hydrogen Energy Earthshot Initiative, RFI, or Request for Information, looking to gather information on potential demonstrations, deployment projects, including spanning all pieces of the hydrogen value chain, production, infrastructure, end uses, etc. Got a lot of responses, I think 200 plus responses from all across the spectrum: industry, investors, academia, laboratories, other stakeholders, etc. But focusing on four main topics here. So first, regional hydrogen production resources, infrastructure in various regions for producing and utilizing hydrogen. What are the end users in those various regions? And what is the greenhouse gas or pollutant emissions reduction potential of the technologies considered there? There's a significant segment looking at diversity, equity, and inclusion, or DEI, jobs production, and environmental justice. And then looking again at the science and innovation needs and challenges. So, as I mentioned, they received 200 responses or more from this RFI. There's sort of an overview of the things that were learned from this, and there's really opportunities to produce clean hydrogen all across the U.S. To really look at kind of showcasing the diversity of resources and industries, and even the communities that we have in our nation here. So, just to select a few examples, so California, currently very active in hydrogen, very diverse population, but they also have a significant hydrogen hydrogen vehicle program ongoing already. I'll say the Southwest and the Gulf Coast have a lot of solar resources. Mentioned already a lot of hydrogen utilization already in the Gulf Coast with the existing hydrogen pipeline, and certainly a chemical industry that could readily utilize that hydrogen. In the Pacific Northwest and New England, a lot of potential for offshore wind to be used for hydrogen generation. There are smaller communities that could be utilizing that hydrogen. Tribal communities, Pacific Northwest in particular, fishing communities in New England, and a lot of workforce available there as well. So within the central U.S., I'd say the Great Lakes and Appalachian regions as well. Of course, a lot of fossil energy resources, nuclear energy, and a lot of other resources, and fabulous workforce for getting that implemented as well. Finally, the Alaska and Hawaii have, of course, very unique geographics and unique opportunities. Again, a lot of fossil resources in Alaska and a lot of solar and wind resources in Hawaii that can be used for hydrogen production and assistance with providing power for isolated communities in both cases. Just want to focus real quickly on Appalachia. I need to run through this quick. I'm not going to read through everything on this slide, but we do have a lot of great resources within Appalachia for generating a hydrogen hub here. Of course, we have the fossil resources in the region, particularly natural gas, are very extensive and would make a great resource for generating hydrogen. In addition, we have a lot of carbon capture, I'd say a lot of geology that's relevant to carbon capture. So transforming that natural gas into hydrogen, capturing the carbon and storing that underground can all be readily done within the Appalachian region. Note there are a lot of distressed communities with high unemployment rates, in part due to reduction in coal utilization across the country. So a valuable workforce that, again, can really help us accelerate any hydrogen economy within the Appalachian region here. The last thing I'm going to touch on here is our bipartisan infrastructure law, or the BIL for short. This was a law signed, I think it was in mid-November, but includes about almost $10 billion for clean hydrogen across the country. That includes about $8 billion for at least 4 regional clean hydrogen hubs, about $1 billion for electrolysis R&D, trying to drive the cost of electrolysis down to about, the goal for that particular program is to get it down to $2 per kilogram by 2026. There's $500 million for a clean hydrogen technology manufacturing and recycling research program as well. So a lot of money to be pumped into the economy and local and regional economies to achieve these goals. So talk a little bit more about the hydrogen hubs. What is a hydrogen hub? It's the definition, at least, is sort of a network of clean hydrogen producers, potential clean hydrogen consumers, and connected infrastructure located in close proximity. So to kind of break that down a little bit, the purpose of those hubs, again, to aid in the achievement of clean hydrogen production. There's a standard that was set forth in the bill that that hydrogen should be able to attribute less than 2 kilograms of CO2 per kilogram of hydrogen to qualify as clean. And you also need to demonstrate production, processing, delivery, storage, and use of clean hydrogen, essentially everything in the hydrogen value chain within that hub. The ultimate goal here is to take the regional hydrogen hubs and eventually coalesce them into a national clean hydrogen network to facilitate a clean hydrogen economy. Last thing I'll mention here are some of the criteria for the hydrogen hub selections. There needs to be diversity in feedstock, so we need at least one hydrogen hub each that's focused on fossil fuel hydrogen production, hydrogen from renewable energy, and hydrogen from nuclear energy. At least one of each hub needs to look at hydrogen use in the electric power generation sector, the industrial sector, residential and commercial heating sector, and the transportation sector. So a lot of diversity in feedstocks, a lot of diversity in end uses, but also looking for geographic diversity, as we've seen in the previous couple of slides. A lot of different resources around the country, where these can be utilized. There is a provision to have at least 2 hubs in natural gas producing regions of the U.S. So Appalachia would be a prime example. Gulf Coast probably another. We have a couple other regions, say in the Wyoming, North Dakota areas, kind of down through Oklahoma, Texas, a lot of other natural gas producing regions in the country as well. Employment, there is a provision to select hubs based in part on the opportunity to create skilled training and long-term employment for the greatest number of residents in the regions. So should be, I think, a lot of money coming in to not only help build the hydrogen hubs, but create a workforce that's capable of sustaining that for the long term. So I think this is one of my last slides here. The job opportunities involved with hydrogen hubs, et cetera. So types of jobs that'll be needed. Certainly we'll have hydrogen production plants that'll require fossil electrolysis. We'll need construction and operations staff to build and operate those plants. End-use utilization of hydrogen in plants and applications, whether it's utilizing hydrogen in, say, gas turbines, fuel cells, the transportation industry, or even, say, steel or cement manufacturing. We need people to build those plants, to operate those plants as well. And likewise, to do this I would say economically, we'll need a significant hydrogen infrastructure, likely with pipelines, in some cases retrofit for hydrogen, sometimes purpose-built for hydrogen, new hydrogen pipelines. I've mentioned already the need for geologic storage. We need to store that hydrogen, so typically it will generate more hydrogen in the summer and we'll need to utilize more in the winter. So we need to save hydrogen probably in the subsurface for that purpose. Of course, there'll be other needs for storage, hydrogen storage in above ground applications as well. So jobs needed to build out all of that infrastructure and operate it. So some of the skills needed, process plant engineering and design. We need power, chemical, or industrial plant construction and operations trades. Some of those that Anthony's mentioned already, engineering, prototype building, and testing capabilities. And then finally, pipeline construction, operations trades, as I mentioned on the hydrogen infrastructure piece. Some mining trades as we start to look at the subsurface pieces as well, salt caverns, subsurface storage, etc. And then, hydrogen is known as it is, more explosive. It's more reactive than natural gas. So there are a lot of safety measures that need to be put in place as well. So people that can provide and implement hydrogen safety measures, I think are across all segments of the value chain, I think are also going to be high demand. So with that, I think I will close the presentation and open things up for discussion.
Thanks, Nate. That's great. We usually have a little section at the end of these to talk a little bit about the workforce implications and economic development implications of the technologies and the main struggles with the technologies themselves. But you did a great job of including them in the presentation. So just let me see if I can move out from your presentation to our end slide. Yeah. So I think you touched upon some of the workforce implications, but I did have one technical question. Kind of, when you're working on this from the different feedstock perspectives, are there common research barriers that all of y'all are working on, like all the other labs that are working on hydrogen from the solar perspective or from the nuclear perspective? Are there common elements that you guys are working on together to try to solve? Is there like some end? It's like, are they very, very particular for each technology?
They're somewhat particular. I'll say,
Okay.
Pretty much everybody's working on all the downstream pieces, right? The hydrogen infrastructure, end uses, etc. But we do have more work specifically to us on the fossil-based hydrogen production. The electrolysis is fairly common amongst other laboratories. Ourselves, National Renewable Energy Laboratory, Idaho National Laboratory, all working on electrolysis because you can utilize electricity that's produced from any production method, fossil-based electricity, renewable-based electricity, nuclear-based electricity to use an electrolyzer to make hydrogen. So there are I would say larger programs amongst the national laboratories to kind of collaborate on the electrolysis piece.
We have one question about what about running fuel cells in reverse to produce hydrogen? Is this technique utilized? Cost?
Yeah.
Okay.
Yeah. So there are reversible solid oxide cells. You can take a cell and make hydrogen in electrolysis mode, store that hydrogen, and utilize it later to produce power in a power producing mode. There are some challenges to that, so it's sort of a toss up right now as to whether it's more cost effective to do that as it is to have a separate electrolyzer, which is more efficient at its electrolysis piece, or a fuel cell that's more efficient at its own energy production piece than it is to have them combined in a single cell. So, because you do give up some efficiency as you combine those two technologies into one cell. So it is something we're looking at. I'd say the jury's out as to which one's going to win, but we are working on both aspects of that.
So we have a question about we concentrated mostly on domestic production and use. We have a question. I'm going to try to shorten it because of time. What do you think about export kind of potentials, and is there additional infrastructure necessary for exporting hydrogen?
Yeah, so a lot of mostly exports of hydrogen occur through, I would say, ammonia would be the main energy export. So, so Japan, for instance, and even South Korea, they don't have their own energy resources. They import all of their energy. They're trying to decarbonize, and it's, as I mentioned, it's really expensive and difficult to transport hydrogen. So, actually, more economic to turn that hydrogen into ammonia, put that on a tanker truck and ship it out, and utilize that ammonia directly as an energy source. It does have fuel content. We're working on how to burn ammonia in a gas turbine, for instance, so to generate power. So yeah, go ahead.
So we have two more questions. I want to try to get them in since we have a minute. Does the clean hydrogen production standard of 2 kilograms CO2 per kilogram H2 include upstream methane emissions?
So it depends on whose definition you look at. So the definition in the bipartisan infrastructure law, that centers only that's 2 kilograms only at the plant gate. So where you're producing the hydrogen, it does not include anything upstream, methane emissions wise, nor does it include the greenhouse gas profile of whatever electricity you're using, right? If the electricity is made from a coal power plant versus a wind farm, for instance, it's not accounted for, at least in terms of the clean hydrogen produced in the hydrogen hubs. But they are developing separately clean hydrogen, I guess a renewable standard for clean hydrogen, where it would be a production tax credit, essentially. And so that's, I would say, separate, and some of those do incorporate or look at upstream issues. So reducing natural gas methane emissions in upstream infrastructure is a significant concern in that case.
And one last very general question, and you covered this a little bit. What specific roles for NETL do you envision under the bill for hydrogen hubs and hydrogen R&D? Will NETL issue the competitive FOAs and make the awards, or will NETL have an opportunity to collaborate with industry stakeholders and project implementers?
Yeah, great question. So in that bill, NETL has a role. Actually, we're written into the bill that we need to provide a data clearinghouse and coordination role with regards to hydrogen hubs and with regards to the clean hydrogen manufacturing and recycling program. So we will be collecting data from project performers, distributing that to those who might need it, analyzing that data on behalf of DOE. There is a separate $1 billion clean electrolysis program where we will likely perform actual R&D to help bring electrolyzer costs down there. So, and then still working out whether or not we'll be allowed to work with industry, or how we can work with industry to either help write proposals or provide technical assistance. There's still a few issues to work out with making sure we don't have for ourselves a conflict of interest in terms of both evaluating proposals, for instance, and being a project performer or a proposer. So we may need to.
We only have one question left. Can we try, Anthony? Can we try to get through the last question just because we have a couple minutes?
Yeah. All right, go ahead. Absolutely. If people have to drop off, it's fine. We're recording them, so it's all good.
So there's high demand in Europe for procurement of technologies for producing green hydrogen. Could you please compare the market positions and export potential of U.S. hydrogen technology producers with major foreign competitors? And this will be the last one, guys, but I don't know. That's very complex, but if you can give it a shot.
Yeah. So yeah, they are, I would say, much more heavily invested in green hydrogen in Europe. Part of that's due to high gas prices, high natural gas prices. And of course, everyone's sort of phasing out coal in Europe. So, in that context, they're expected to, green hydrogen's expected to be able to compete or beat, blue hydrogen or fossil-derived hydrogen much more quickly in Europe than it is here. So, because of our low natural gas prices, it's likely that we'll have, blue hydrogen should be the winner for a while, at least in some regions of the country. So, so we are working on electrolyzer technology that's developed anywhere would work, here, work in Europe, etc. So, we do have producers here that are working in Europe and vice versa. In terms of exports of hydrogen, again, hydrogen is not readily exported in its current form. It takes a lot of energy to compress it. It takes a lot of energy to liquefy it if you want to transport it. So, again, if we did shipments to Europe, it would probably be in the form of ammonia. But as I said, the higher demand for ammonia is coming currently from Japan and the Far East. So, but not out of the question that we might do that in the future.
Great, and she meant it in the form of equipment, but I think we
Okay.
but
All right.
yeah, this is great. It shows the big interest in hydrogen and hydrogen technology. Again, thank you very much, Nate, for your time. Thank you for walking through the industry bill a bit. The the hydrogen shot, which I always think of as the sun shots at lower prices.
Yeah.
But anyways, and thank you for your time. And Anthony, any final words?
Echo those statements. Thanks everyone for joining us today. I thought it was a really good discussion led by Nate. And we recorded this, so we will edit it and post it to our RWFI page here in the coming days. So thanks again, everyone. Talk to you later.